We are all time travelers, every single one of us. You don't need a fancy shimmering machine with blinking lights and whirring gears to embark on this journey. You are on it right now, as you read these words. We are all passengers on a cosmic vessel we call Earth, hurtling through the vast, dark ocean of space-time. Our journey is relentless, moving ever forward into the future. The rate of our travel is so constant, so familiar, that we barely notice it. We call it 1 second per second. It's the steady, reliable rhythm of a universal clock, ticking away the moments of our lives, from birth to this very instant, and onward to whatever comes next. It's the most profound, yet most overlooked adventure of all. Think about it. You can move in any direction you choose in space. You can walk left or right, you can jump up, you can crawl down. You have 3 dimensions of spatial freedom, but in the 4th dimension, time, you have no such choice. You are carried along a one-way current, an unseen river that flows from the past, through the present, and into the unknown territory of the future. You can't stop it. You can't reverse it. You can only experience it, moment by moment. This shared universal experience of time's arrow is what binds all of humanity together. A silent agreement that tomorrow will follow today, just as today followed yesterday. This constant forward motion feels absolute, like a fundamental rule of the cosmos that can never be bent or broken. For most of human history, we believed just that. Time was a grand cosmic clock, ticking at the same rate for everyone and everything, everywhere in the universe. It was the ultimate constant, a rigid backdrop against which the drama of life and the motion of the stars played out. It was simple, intuitive, and comforting in its predictability. But as we began to ask deeper questions about the nature of reality, about light and gravity, we stumbled upon a truth that was far more strange and wonderful than we could have ever imagined. Our comfortable, everyday understanding of time was about to be shattered. The universe, it turns out, is a much wilder and more flexible place than our limited senses would have us believe. A young patent clerk, with nothing but his mind and a few thought experiments, would soon show us that the river of time is not the same for everyone. It can speed up and slow down. It can be stretched and squeezed. The journey through time is not a simple straight line. It is a personal, relative experience, unique to every traveler. And that realization changed everything we thought we knew about the cosmos. At the dawn of the 20th century, a brilliant mind named Albert Einstein completely rewrote our understanding of space and time. He showed us that they are not separate, independent concepts. Instead, they are woven together into a single 4-dimensional fabric of space-time. And this fabric is not rigid, it is dynamic and malleable. Einstein's theory of special relativity was built on 2 simple but powerful ideas. First, the laws of physics are the same for everyone, no matter how fast they are moving. Second, the speed of light in a vacuum is the ultimate cosmic speed limit, a constant that never changes, regardless of who is measuring it. These 2 ideas led to a mind-bending conclusion. Time itself must be relative. It must stretch and contract depending on your motion. Imagine you are on a spaceship traveling at a significant fraction of the speed of light. From your perspective, everything inside your ship seems perfectly normal. Your watch ticks at its usual rate. Your heart beats steadily. But for someone watching you from Earth, things would look very different. They would see your clock ticking much, much slower than their own. This isn't an illusion or a trick of perception. Time itself is genuinely passing more slowly for you. This effect is called time dilation. This means there is no single universal now. The rate at which you experience time depends on how fast you're moving through space. The faster you travel through space, the slower you travel through time. It's as if you have a certain budget of motion through space-time. If you spend more of that budget on moving through the 3 spatial dimensions, you have less to spend on moving through the 1 dimension of time. This interconnectedness is the heart of relativity. It's a cosmic trade-off, a fundamental rule of the universe that links our journeys through space with our passage through time in a deep and inseparable way. Einstein took us from a universe where time was like a metronome, ticking with an unchangeable beat for all, to a universe where every person, every planet, and every galaxy has its own personal clock. These clocks tick at different rates, depending on their motion and their environment. The idea that you could travel into the future simply by moving very, very fast was no longer the stuff of fiction. It became a scientific possibility, a direct consequence of the laws of nature. Einstein had not just given us a new theory of physics, he had given us a new vision of reality itself, one where time was a character in the cosmic play, not just the stage. To understand why time must slow down for a moving observer, let's use one of Einstein's favorite tools, a thought experiment. Imagine a clock, but not one with gears and hands. This is a light clock. It consists of two mirrors, facing each other, with a single particle of light, a photon, bouncing between them. Each time the photon hits a mirror, the clock ticks. Now let's put this clock on a stationary platform. The photon travels a certain distance, straight up and down, between the mirrors. The time between ticks is very simple. It's the distance divided by the speed of light. It's a steady, predictable rhythm. Now, let's put that same light clock on a rocket ship that is flying past you at an incredible speed. From the perspective of someone on the rocket, the photon is still just going straight up and down between the mirrors. Nothing has changed for them. But from your perspective on the ground, things are different. As the photon travels from the bottom mirror to the top mirror, the entire clock has moved horizontally. So, you don't see the photon travel in a straight line up and down. Instead, you see it travel along a longer diagonal path. This is a crucial point. The path you observe is longer than the path the person on the rocket observes. Here is where the magic of relativity comes in. Remember one of Einstein's core rules. The speed of light is constant for everyone. It doesn't matter if you're standing still or moving at 1,000,000 miles an hour, light always travels at the same speed. So from your viewpoint on the ground, the photon in the moving clock has to travel a longer diagonal distance. But it cannot travel any faster to make up for that extra distance. Since its speed is fixed, the only way it can cover that longer path is if it takes more time to do so. This means that from your perspective, the moving clock must be ticking slower. This isn't a mechanical flaw in the clock, it's a fundamental property of time itself. Any clock, whether it's based on light, atoms, or a beating heart, would behave in the same way. The flow of time itself must slow down for the moving observer to keep the speed of light constant for everyone. This simple thought experiment reveals the profound connection between space, time, and the speed of light. It shows us that our intuitive notions of a single, universal time are wrong. The universe operates on a set of rules that are far more elegant and strange, where your experience of a second depends entirely on your journey through space-time. Thought experiments are powerful tools for the mind, but science demands real-world evidence. We need to test these incredible ideas. In 1971, two physicists named Joseph Huffell and Richard Keating did just that. They took several incredibly precise atomic clocks so accurate they would lose less than a second over millions of years, and synchronized them. They left one clock on the ground at the United States Naval Observatory. They put the others on commercial airplanes and flew them around the world, once eastward and once westward. When the planes landed and they compared the clocks, they found exactly what Einstein's theories predicted. The clocks that flew eastward, moving in the same direction as the Earth's rotation, and thus faster relative to the center of the Earth, had ticked ever so slightly slower than the clock on the ground. They had aged less. The clocks that flew westward, against the Earth's rotation and thus slower, had ticked slightly faster. The differences were minuscule, just a few billionths of a second, but they were real, and they matched the predictions of relativity perfectly. This was the first direct, macroscopic test of time dilation. Humanity had built clocks, sent them on a high-speed journey, and measured a real physical difference in the passage of time. But the proof doesn't stop with flying clocks. We see evidence of time dilation every day in the world of particle physics. There are subatomic particles called muons, which are created when cosmic rays from space slam into our upper atmosphere. Muons are incredibly unstable. They have a very short lifespan, decaying into other particles in just 2.2 microseconds, or 2.2 millionths of a second. Even traveling at nearly the speed of light, they should only be able to travel about 660 meters before they decay. Based on this, very few muons created high in the atmosphere should ever reach the Earth's surface. And yet, we detect them down here on the ground all the time. Why? Because of time dilation. From our perspective, these muons are moving at over 99% of the speed of light. At that incredible velocity, their internal clocks are ticking much slower than ours. What feels like 2.2 microseconds to the moon is stretched out to a much longer time for us on Earth. This extra time allows them to survive the long journey down through the atmosphere to our detectors. The constant rain of muons on the Earth's surface is a beautiful, ongoing experiment that confirms Einstein's strange and wonderful vision of time is, in fact, the reality we live in. You might think that Einstein's theories of relativity are abstract concepts, relevant only to physicists and astronomers thinking about black holes and the Big Bang. But the truth is, relativity is at work all around us, and you probably use it every single day without even realizing it. If you've ever used a GPS device in your car or on your phone to find your way, you've relied directly on Einstein's insights into the nature of space-time. Without accounting for the effects of relativity, the entire global positioning system would fail within minutes, accumulating errors that would make it utterly useless for navigation. The GPS network consists of a constellation of satellites orbiting high above the Earth. Each satellite carries a highly precise atomic clock. To determine your location, your GPS receiver on the ground picks up signals from at least 4 of these satellites. By measuring the time it takes for the signal from each satellite to reach it, your receiver can calculate its distance from each one and triangulate your exact position on the globe. This process requires timing accuracy down to a few nanoseconds, a few billionths of a second. But here's the catch. The clocks on the satellites and the clocks on the ground experience time differently. There are 2 relativistic effects at play. First, because of special relativity, the satellites are moving at about 14,000 kilometers per hour relative to us on the surface. As we learned from the light clock, moving clocks tick slower. This effect of time dilation would cause the satellite clocks to lose about 7 microseconds or 7,000 nanoseconds every single day compared to clocks on Earth. It's a small amount, but enough to throw off the system. If this were the only effect, GPS engineers could easily correct for it. But there is another, even more powerful effect to consider, one that comes from Einstein's other great theory. That second effect is gravitational time dilation, which we will explore more deeply. In short, clocks in a weaker gravitational field tick faster. Since the GPS satellites are far above the Earth, they experience weaker gravity than we do. This causes their clocks to tick faster than ours by about 45,000 nanoseconds per day. When you combine the 2 effects, the net result is that the clocks on GPS satellites run faster than ground-based clocks by about 38,000 nanoseconds daily. The engineers who designed the GPS system knew this. They built the system to constantly correct for this relativistic time difference. Without that correction, your GPS would be off by about 10 kilometers every single day. Einstein wasn't finished after special relativity. He spent another decade wrestling with a bigger idea, gravity. His theory of general relativity, published in 1915, presented a completely new picture of gravity. It wasn't a force pulling objects together, as Isaac Newton had described. Instead, Einstein proposed that massive objects warp or curve the very fabric of space-time around them. Imagine placing a heavy bowling ball on a stretched-out rubber sheet. The ball creates a deep dimple in the sheet. Now, if you roll a small marble nearby, it won't be pulled by the bowling ball. It will simply follow the curve in the sheet created by the ball. This curvature of space-time doesn't just affect the motion of objects, it also affects the flow of time itself. According to general relativity, time runs slower in stronger gravitational fields. The deeper you are in a gravity well, the slower your clock will tick, compared to a clock in a weaker gravitational field. This effect is known as gravitational time dilation. It means that a clock at sea level will tick ever so slightly slower than a clock on top of a mountain, because the clock at sea level is closer to the center of the Earth and in a slightly stronger gravitational field. The difference is incredibly tiny, but it is real and measurable. This has some fascinating consequences. It means that your head is technically aging a tiny bit faster than your feet, because your head is farther from Earth's center of gravity. Of course, this difference is so small it's completely unnoticeable in our daily lives. But near objects with immense gravity, like a neutron star or a black hole, these effects would be dramatic. If you could hover in a spaceship near the event horizon of a black hole, the point of no return, time for you would slow to a crawl, compared to time for someone far away. You might experience only a few hours while centuries or even millennia passed for the rest of the universe. This warping of time by gravity has been confirmed by numerous experiments. We already saw its crucial role in making GPS technology work. Scientists have also measured it directly using atomic clocks placed at different altitudes. In one experiment, physicists at the National Institute of Standards and Technology used two incredibly precise clocks, placing one 33 centimeters higher than the other. They were able to measure that the higher clock ran just a little bit faster, exactly as Einstein's theory predicted. Gravity's grip on time is not just a theory, it's a fundamental aspect of our physical reality, shaping the rhythm of the cosmos from our own planet to the most extreme objects in the universe. Once we accept that time is flexible, a natural question arises: can we bend it enough to travel backward? Einstein's equations of general relativity allow for some very strange and exotic possibilities. One of the most famous is the concept of an Einstein-Rosen bridge, better known today as a wormhole. A wormhole is a theoretical shortcut, a tunnel through the fabric of space-time that could connect two very distant points in the universe. You might enter a wormhole in our galaxy and emerge moments later, in a galaxy millions of light-years away. It would be the ultimate cosmic shortcut, saving you an impossible journey through normal space. But what if a wormhole didn't just connect two different places in space, but also two different moments in time? In theory, this might be possible. Imagine you have a wormhole with two mouths, A and B. You leave mouth A stationary and take mouth B on a high-speed round trip, similar to the thought experiment with the traveling twin. Because of time dilation, less time will have passed for mouth B than for mouth A. When you bring mouth B back, it might be synchronized with the year 2050, while mouth A is still in the year 2060. If you then stepped into mouth A in 2060, you could emerge from mouth B in 2050, effectively traveling 10 years into the past. This kind of structure, which allows for travel into one's own past, is known in physics as a closed time-like curve, or CTC. It's a path through space-time that begins and ends at the same point in both space and time, forming a loop. A wormhole that has been manipulated in this way would be a time machine. The mathematics of general relativity doesn't forbid these structures from existing, but that doesn't mean they are easy to create. In fact, building a stable, traversable wormhole would present some of the most formidable engineering challenges imaginable, requiring physics that we don't yet fully understand. The primary obstacle is the need for something called exotic matter. To keep the throat of a wormhole open and prevent it from instantly collapsing into a black hole, you would need a substance with negative energy density or negative pressure. This is not like any matter we have ever observed in the universe. While some quantum effects can produce tiny, fleeting amounts of negative energy in a lab, we have no idea how to gather or stabilize enough of it to prop open a tunnel through space-time. So, while the laws of physics may leave the door to the past slightly ajar in theory, the practicalities of building the key make it a near impossibility for now. Let's imagine for a moment that we could overcome the immense technological hurdles. We've found our exotic matter, we've built our wormhole time machine, and we are ready to step into the past. This is where we run into a new set of problems, not of engineering, but of logic. These are the famous paradoxes of time travel. The most well-known is the grandfather paradox. What if you travel back in time and prevent your own grandparents from ever meeting? If they never meet, then one of your parents is never born, which means you are never born. But if you were never born, how could you have gone back in time to stop them in the first place? This is a direct contradiction, a logical knot that seems to defy a simple solution. It suggests that any action you take in the past that prevents your own time travel would create an impossible situation. Another related problem is the consistency paradox or the bootstrap paradox. Imagine a scientist who gets the plans for a time machine from a future version of herself. She builds it, uses it, and eventually travels back to give the plans to her younger self. The question is, where did the information for the plans originally come from? It seems to have been created out of nothing, existing in a self-contained loop with no origin point. Some physicists believe that these paradoxes are a sign that travel to the past is simply forbidden by the laws of nature. The universe might have a built-in chronology protection mechanism that prevents such logical inconsistencies from ever occurring. For example, perhaps any attempt to create a wormhole time machine would cause a runaway feedback loop of energy that would destroy it just before it became operational. The universe, in this view, actively polices its own history to ensure that cause always precedes effect, preserving the logical structure of reality as we know it. History, it seems, might have a way of fighting back. Another possible solution is the many worlds interpretation of quantum mechanics. In this view, any action you take that would change the past doesn't alter your own history. Instead, it causes the timeline to split, creating a new parallel universe. So if you went back and prevented your grandparents from meeting, you wouldn't vanish. You would simply have created a new timeline where you don't exist. But you would continue to exist, now as a visitor in this alternate reality. This neatly resolves the paradox, but it comes at the cost of an infinite number of parallel universes branching off with every quantum event, a staggering and unprovable idea. The dream of mastering time is as old as human consciousness itself. Long before Einstein gave us the science, storytellers gave us the vision. H.G. Wells' The Time Machine, published in 1895, sent a Victorian gentleman into the far future to witness the evolution and eventual demise of humanity. This tale and countless others that followed planted the seed of time travel deep within our collective imagination, from the whimsical adventures of Doctor Who in his TARDIS to the paradox-laden antics of Marty McFly in Back to the Future. Science fiction has explored the hopes, fears, and profound questions that time travel raises. These stories do more than just entertain us. They serve as grand thought experiments, allowing us to explore the potential consequences of such a powerful technology. They grapple with the ethical dilemmas. Should we change the past to prevent a tragedy, even if it has unforeseen consequences? They warn us of the dangers of paradox and the fragility of history. In many ways, science fiction acts as a cultural laboratory, stress-testing our ideas about causality, free will, and our place in the cosmic timeline. It inspires young scientists and pushes the boundaries of what we dare to ask about the nature of reality. Today, the quest to understand time continues on the frontiers of physics. Quantum mechanics, the science of the very small, adds another layer of strangeness. Concepts like quantum entanglement, where two particles can be linked in such a way that they affect each other instantly over vast distances, challenge our classical notions of space and time. Some physicists are even grappling with the problem of time, where in certain quantum equations of the universe, the variable for time seems to disappear entirely, suggesting that our experience of time's flow might be an emergent property of a deeper, timeless reality. So where does that leave us on our quest? We know that time travel to the future is not only possible, it's an undeniable fact of our universe, proven by experiment. You can buy a one-way ticket to the future. All you need is a very, very fast ship. But travel to the past remains a far more difficult, perhaps impossible proposition, guarded by paradoxes and the need for physics beyond our current grasp. As we develop new tools, from more powerful particle accelerators to sophisticated artificial intelligence that can probe the complex equations of reality, our understanding will deepen. For now, the past remains a locked country, and the mastery of time remains a dream for the future.